All right, here we go. We find ourselves at Chapter 9, Problem Set 3. This is number 41. Number 41 says, the figure shows a two-ended rocket that is initially stationary on a frictionless floor with its center at the origin of an x-axis. The rocket contains a central block C of mass 6 kilograms and left and right blocks, each of 2 kilograms. Small explosions can shoot either of the side blocks away from block C along the x-axis. Here is the sequence. At time t equals 0, block L is shot to the left with a speed of 3 meters per second relative, this is going to be important, relative to the velocity that the explosion gives the rest of the rocket. Okay, so this is clearly a conservation of momentum type problem. So when we look at this, what we're going to end up with is after the first explosion, our little box over here, which we'll call L, is moving that way, and then these two blocks over here are moving the other way. Now, we don't know what these are, but we know that the velocity is 3, the relative velocity is 3. That means this one could be moving at 1 and this one at 2, or this one at 1/2 and this one at 2.5. But the difference between their velocities is going to be 3. So that's important, okay? That's important. So what it says is the relative velocity is the difference between these two. Now, you might say like, oh, well, it's the addition of these two. But really what it is, it's the V center, and that's center and right, minus the V left. Now, because this one is negative. So basically, if this was like 1 and this was 2, it'd be 1 minus a negative 2, which would give you 3. So this is our statement to start. So how do we work this? Well, let's just start with the general principle. And, well, what do we know? We know that the initial momentum has to equal the final momentum. Luckily for this one, the whole thing starts at rest, so the initial momentum is 0. And the final momentum is going to be mass of the left times the velocity of the left plus the mass of the right and center times the velocity of the right center. So that's this block over here, right and center. We add these together, and so when we subtract here, we end up with, I'm going to put the masses in here, so we end up with negative 2 times VL is equal to 6, that's, 6 plus 2, because it's both of them together, 8 times V RC. Now, I don't know VL or RC. That's probably something I should figure out. But up here, I have this statement here, which is the other statement that I'm looking for. So because I have 2 equations and 2 unknowns, I should be able to solve directly. So I'm actually looking for the VL, so what I'm going to do is I'm going to solve for VR and substitute it in here. So if I look up at this equation here, VRC is going to be V relative plus the VL. Okay. I'm going to take this and substitute this in here. So I have negative 2 VL is equal to 8 times, and then VRC here is the relative velocity plus the VL. So the relative velocity is 3. We got that from the original problem. So the original problem tells us that when this is shot off, the relative velocity is 3 meters per second. So subtract this from both sides, I end up with negative 10 VL is equal to 24. So VL is equal to negative 2.4 meters per second. Now, that makes perfect sense to me. It's moving this way at 2 meters per second. What does that tell us about the V of the CR then? Well, if I know that, oh, I forgot the negative. If I know that VCR minus VL is equal to 3, so I'm going to use this equation right here, or this equation right here. So minus a negative 2.4, that tells me that the VCR, okay, so this is 3 is equal to something minus negative 2.4, so there's got to be 0.6 meters per second. And this also makes sense because if you think about it in a speed context, this here, if this one's moving to the right at or left at 2.4 and this one's moving to the right at 0.6, this one right here is 4 times as massive, so it has 1/4 the speed. So the momentum seems like it works out okay. The second part of the problem says that at time t equals 0.8 seconds, block R is shot off at a speed of 3 meters per second relative to the velocity that the block C has. So we're going to use a similar concept here. All right, we're going to ignore the left block now, and we have these two blocks here. So what's interesting about this one is that in the after picture, let's look at the before picture first. Here's the before picture, and what we got out of the last one was that this whole thing is moving to the right at 0.6 meters per second. So we're going to use a conservation momentum statement again. So this is the before picture. Now, the after picture for this one, which I find really interesting, is going to have this car again, or this block again, and it says that it shoots it off. It says that it shoots it off at 3 meters per second relative to the after speed of this guy. So I don't know actually whether after this, we know that they're moving apart from each other at relative 3 meters per second, but I don't know if this one is still moving to the right and this one's moving to the right just 3 faster, or this one's moving to the left and this one's moving to the right and the difference between them is 3. I don't know, we're gonna have to work it out, but we're gonna start with the same couple statements here where, so similar to the last one, we're gonna start with a relative velocity statement. So this time, this is the relative velocity between them, and it's just like the last one. We're going to use the velocity of the R minus the velocity of the C. And we're also going to use a conservation momentum statement. So the conservation momentum this time, we know that P PI is equal to PF, the initial momentum has to equal the final. So before, the momentum was this. It was the mass of the center plus the mass of the right, and they're moving together at the velocity of the right center. Afterward, they're individual, so then it's the mass of the center times the velocity of the center plus the mass of the right times the velocity of the right. So again, we can put the masses in. We know the velocity of right center, okay, because we solved for that in the last problem. We don't know either of these, but we have two equations and two unknowns. So let me put the mass in to make it a little bit easier. So these two is 8. We know this is 0.6. And that's equal to the velocity of the center is 6 times its velocity, plus the mass of the right is 2 times its velocity. And again, I have two equations and two unknowns, so I'm going to put them together. Eight times 0.6 is 4.8. We're going to have to solve for both of these, but I'll solve for the velocity of the right one here. So the velocity of the right is going to be equal to the relative velocity plus the velocity of the center. So, and I'll plug that in down here. So 4.8 is equal to 6 times the velocity of the center plus 2 times, substitute in here, relative velocity plus the velocity of the center. The relative velocity is 3, 2 times 3 is 6, plus 2 times the velocity of the center. I'm going to combine like terms, so I'm subtract 6 from both sides. So 4.8 minus 6 is negative 1.2 is equal to 8 times the velocity of the center. Now, one thing I like about this is you're going to notice right away here that we have a negative value here, which seems like all of a sudden now this might be moving backward. So if I divide here, the velocity of the center is negative 0.15. And then if I want to solve for the velocity of the right, I could use this up here. This is 3 plus a negative 0.15. So that's got to be 2.85 meters per second. So after the collision, this one's moving to the right at 2.85. This one actually turns out is moving to the left at 0.15 meters per second. The last question basically asks for where is the center? So where is this center block right here? Well, so we know a couple things. At t equals 0, it starts moving, the centerpiece is moving at 0.6 meters per second. And it does that for 0.8 seconds. Then at t is equal to 0.8, the velocity switches to negative 0.15, and it does that for delta t is equal to 2 seconds. So when I put these two things together, I get, so this is, so the change in position is going to be the delta x from the first one. So 0.6 times 0.8 is 0.48. That's how far I moved in the first 0.8 seconds. And then in the next 2 seconds after that, it's going at negative 0.15 for 2 seconds, which is going to be a negative 0.3. And so it went 4.8 to the right and 0.3 to the left. So the total change in position, which is also then going to be the position because it started at 0, is 0.18 meters. All right, let's look at 45. So it says a 20 kilogram body is moving through space in the positive direction with a 200 meters per second speed due to some internal explosion. It breaks into 3 parts. One with a mass of 10 kilograms moves away from the point of explosion. And then it has some other things. So this is unit vector notation. What is the velocity of the third piece? How much energy is released in the explosion? Ignore effects due to gravitational forces. Okay, so this is going to be a conservation of momentum type situation. So the original body is 20 kilograms moving through space. Okay, it's moving through space at 200 meters per second. So we can see what the initial momentum is. Then it says it's going to break up into 3 pieces. Okay. One part with a mass of 10 kilogram moves away from the point in the positive y direction. So that means that this one is going to have velocity that's straight up. So this is a 10 kilogram piece, and it's moving with a speed of 100 meters per second. Okay, that's one piece. A second part with a mass of 4 kilograms moves in the negative x direction with a speed of 500. So we have another piece. Ooh, let's make that one green. So it's moving in the negative x direction at like 500 meters per second. And its mass is 4. Then it says, find what is the velocity of the third part. Okay, so here's what's interesting. If I think about this, we know the total momentum before has to equal the total momentum after. So let's draw some momentum vectors here. So if I put my momentum vector in for this guy here, it's 200 meters per second times 20 kilograms. So that's 4,000. So this is the initial momentum. Pi is equal to 4,000. Now the Pi has to equal the PF. What do we have after is the question. So this is 100 times 100 now, but it is in the positive y direction. So if I put that here, this is 10 times 100, that's 1,000. So this is part of the PF, this is 1,000. Okay, this one here, it's 500 times 4. That's 2,000. So I know that when I add this, and the third one, it has to equal this thing here, correct? So I know that this is up and left, but the total has to be all right, which means that this has to be down enough to cancel the up, right enough to cancel this out, and add this together. So when we think about it, we can think about it from a vector subtraction way, or we can think about it from a vector addition methodology. But what I do know is that this plus the other one has to somehow equal this one right here. So this one is, so what does our final have to be? It's got to be 4,000, correct? So I'm going to draw it over here. Which means that the third piece momentum has to be this long and this wide. Oh, actually, that's a total lie. It has to cancel out this one. And this way. So if I draw this, let's see if I can draw it here. I need to draw it from here to here. Let's see if we can figure out what the situation is here. So I know that the down has to be 1,000 kilograms meters per second for that momentum. And this has to be enough to cancel out the 2,000 and add to 4,000. So this has to be 6,000 kilograms meters per second. So if I want to get the total momentum, I'm going to use the Pythagorean theorem there. So 1,000. So we're going to call this P. So P squared is equal to 1,000 plus 6,000. And if I use the Pythagorean theorem there, I end up with 6,083 kilograms meters per second. And then the question is, what is the velocity of this piece? And so then what I have to do is I have to, because P is equal to mv, I have to divide by the mass of this piece. So this was 20 kilograms to start. This one's 10, this one's 4, so I'm left with 6. Okay. So if I want to divide each of these by 6, I could actually get the speeds there. So This one then, the velocity would be equal to 1,000 divided by 6, which is 167 meters per second in that direction. 6,000 divided by 6, this would be 1,000 meters per second in that direction. And I think it asks for it in unit vector notation. So this would be 1,000 I minus 167 J. Now, the next question is, how much energy is released in the explosion? And so to find that out, what we're going to do is we're going to just compare all the initial energy to all the final energy and see what the situation is. Let me get rid of this so we have some space here. So if I want to get the initial energy, it's all kinetic, so I'm going to use 1/2 mv squared. In this case, it's 1/2 the mass, which is 20 times 200 squared. Okay, put that in a handy dandy calculator. So that's 400,000. So we're starting off with 400,000 joules of energy. Now, what about the after? Well, each of these has kinetic energy, and the kinetic energy direction doesn't matter. So if I want to get the kinetic energy of the blue one, 1/2 the mass is 10, times the speed is 100. So that's 50,000. The mass of the green one, the mass is 4, speed is 500. It's 500,000. And then what about the red one? Well, in order to get the red one, I actually need to figure out what the speed is in this direction. Now, I know the momentum in that direction, so if I divide that by 6, so the speed is 1014 meters per second. So I have 1/2, the mass is, what did we decide the mass was? 6 times 1014 squared. Okay, I'm going to put that in the calculator. So that one is 3,084,588. So if I add all these up, and what the total after was 3,634,588, and the initial was 400,000. So it looks like we added 3, 2, 3, 4, 5, 8 joules in the explosion. All right, we're on to problem 51. 51 says a 3.5 kilogram bullet, that's going to be important. It says 3.5 grams. So always when you're working here, you got to work in kilograms. So 0.0035 kilograms. It's fired horizontally at 2 blocks, initially at rest. The bullet passes through the first block. So I'm going to call this one M1. So the first block, M1, has a mass of 1.2 kilograms. And the second block, which we're going to call M2, has a mass of 1.8 kilograms. The blocks end up with speeds v1. So after it passes through, speed 1 is 0.63 meters per second. And v2 ends up with a speed of 1.4 meters per second. Neglecting any material moved from the block, find out the speeds as it leaves and enters block 1. Okay, so this is a kind of a backward working problem where, because we know it ended up here, we're going to start here and then work backward, because it's much easier if you work backward. Now, you may not have known that, but I've been doing this a long time, so let's go with that. So let's start with the second situation. We're going to have to write conservation momentum for both of them. So this is for block 2 here. Okay, let's try to figure out what's happening with block 2. Before it enters block 2, put block 1 over here. So we know that the before situation is you have, well, let's start with a general statement. The thing is, we know the momentum is conserved. So we start with a PF equals PI. We know the bullet is moving on its own. So the mass of the bullet times the velocity of the bullet before it hits block 2 is equal to the after situation, m bullet plus mass of block 2 times the velocity of 2. And what's nice about this is we know everything in here to solve. So we know the mass of the bullet is 0.0035. This is actually what we're looking for. .8 and 1.4. So we know all the information we need. Let's see if we can't put it in the calculator. So the velocity of the bullet before it hit block 2 looks like it was 721.4 meters per second. So that's when it was between the blocks. So we're going to assume that it was moving even faster before that. So here's the block 1. Okay, let me make it look a little prettier. So let's do the block 1 situation here. So again, the initial momentum has to equal the final momentum. It's the nice thing about momentum, that's always the same. So what was the before situation? So this was the mass of the bullet times the velocity of the bullet. Now this is way back here, not the between, but the way back. Okay, and afterward, it's the mass of the bullet times the speed of the bullet, velocity of the bullet, plus the mass of block 1 times the velocity of block 1. I know it looks like these are the same, but this is after it passes through and this is before it enters. The nice thing is that this right here, this VB is this VB, and so we can solve directly. Mass of the bullet, 0.0035 times bullet before it enters, times 721, plus mass of this block is 1.2 times its speed after was 0.63. And I think we can solve directly. Put it in my calculator. I got 937 meters per second. So that's the speed of the bullet before it enters block 1. Okay, let's look at 53. This one's weird. It says, in Anchorage, collision of a vehicle with a moose are so common that they're called MVC. That's got to be motor vehicle. How about moose vehicle collision? That's what it's got to be. Suppose a car, 100 kilogram car slides into a stationary 500 kilogram moose on a very slippery road, with the moose being thrown through the windshield. What percent of the original kinetic energy is lost to other forms of energy? Okay, so let's do that here. So what they're implying is an inelastic collision. So again, initial momentum has to equal final momentum. Okay, so what we have here is the mass of the car times the velocity of the car plus the mass of the moose times the velocity of the moose. That's before. And then afterward, since it's thrown into the windshield, we're going to add them together. So we have a 1,000 kilogram car going at some speed v plus a stationary moose is equal to 1,000 plus 500 kilogram moose times the velocity after. Now I'm going to call this MC for moose car because they're now moving together. Okay? And so if I look at this, this is 1,000 So if I solve for the speed afterward, for example, it's equal to 1,000 over 1,500. So what's happening here is it's decreasing, okay? So it's going to be 2/3 of what it was. Now that makes sense because you added on basically 1.5. So you increase the mass by 3/2, but you decrease by 2/3. All right, so now here's the question. Basically it's asking what about the energy? So if you want to know the kinetic energy initial, it's 1/2. The car was the only thing moving initially. So mass of the car, speed of the car squared. That's the initial kinetic energy. The final kinetic energy, 1/2 mass of the car plus the mass of the moose times the velocity of the car moves together squared. Now let's substitute in here because I want to compare this one to this one. So if I substitute in here, I have 1/2. Now I added this on, so this is 3/2 times the mass of the car. And this is 2/3. If I look at this, I end up with 1/2 mass of the car, speed of the car squared. And what's left over is 2/3. And so the kinetic energy after is 2/3 the kinetic energy before. Now, they want to know what happens if this is a camel. No problem. We're going to use the same situation here. Now, the problem is now I have camel and car start with the same thing, but let's just figure it out. So I have the mass of the car times the velocity of the car. This is before. And the after is going to be mass of the car plus mass of, I'm going to put an M again. We know it's a camel, but there's... Okay. So we're going to use the same notation, but we're going to use different masses this time. So I have 1,000. I think it's only 300 this time. Camels are 300, so 1,000 plus 300. So this time, 1,000, 1,300. So this time, it's not as pretty of a fraction here. So it's going to be 1,000 divided by 1,300. So in decimal form, 1,000 divided by 1,300, it's 0.77. Okay. So here, if I look here, if I go back, this was 0.67. This one's 0.77. So because the mass that you ran into is actually less than the previous one, you actually slow down less. Here you lose 2/3 of your speed. Here you only lose 33% of your speed. This one you only lose 23% of your speed. So let's do the energies. Same energy situation applies that the initial kinetic energy is 1/2 mass of the car, speed of the car squared. The final kinetic energy, 1/2 all right, if I substitute in here. So the total mass is 1.3 times the original mass of the car. And the speed here is 0.77. And because 1.3 and 0.77 are reciprocals, one of them cancels and we're left with 0.77 times 1/2. So here what we're noticing is that you end up with 77% of your energy. Here you ended up with 67% of your energy. So the point of the story is, as the mass of the animal you're hitting increases, the loss of kinetic energy decreases. All right, let's go to 55. A 5 kilogram block with a speed of 3 meters per second collides with a 10 kilogram block that has a speed of 2 meters per second in the same direction. Ooh. So a 5 kilogram block collides with a 10 kilogram block. All right, let's draw that up. And it says that it collides. Oh, it doesn't say elastically or not. I think that they're going to imply that they don't stick together, but let's draw it up first. So a 5 kilogram block is going to collide with a 10 kilogram block. Moving in the same direction. Their initial speeds are 3 meters per second and 2 meters per second. So this one's moving at 3 meters per second. This one's moving at 2 meters per second. They're going in the same direction. It's definitely going to catch up. Okay. So this is the before situation. We'll get to the after situation here in a second. After the collision, the 10 kilogram block travels in the original direction, now with a speed of 2.5 meters per second. What is the velocity of the 5 kilogram block immediately after? So the after situation is going to be, we can draw that also. So basically, this one here picked up some speed. Its speed is now 2.5 meters per second, which means that this one gave some of its momentum, so it's going to be somehow slower. Now, we don't know how much slower. That is the actual question, so let's see if we can figure it out. This is a pretty standard conservation momentum problem. Hopefully we can figure this one out. So we don't know the speed here. But what do we know? We know that the initial momentum has to be equal to the final momentum. So I have, can we call these 1 and 2? So I have mass of 1, velocity of 1, that's before, plus mass 2, velocity 2 before, equals mass of 1, velocity of 1 after. I'm going to use this prime here to mean after, plus m2 v2 after. We know most of these things, so this is a 5 kilograms. This one's 10 kilograms. So if I plug and chug this, I have 5 moving at 3, plus 10 moving at 2. I have 5, I don't know it's after. So now I can just go from here. 5 times 3 is 15, plus 20, so 35 is equal to 5v1 after, plus 25. Subtract and divide, v1 after is equal to 2 meters per second. So, and that makes some sense. So I feel pretty good about that. The second question says, by how much does the total kinetic energy of the distance between the two blocks change because of the collision? All right, so we're going to do a kinetic energy before, and we're going to do a kinetic energy after, and we're going to see. So kinetic energy before, 1/2 m1 v1 squared plus 1/2 m2 v2 squared. So if I do this one, 3 squared is 9, 9 times 5 is 45, 45, half of that is 22.5, plus 20. That's the total energy before. The total energy after, the after is 41.25. So we were at 42.5, and now we're at 41.5. So we lost 1.25 joules. The next part, so the next part says, Suppose instead that the 10 kilogram block ends up with a speed of 4 meters per second after. What is the change in total kinetic energy this time? All right, so what we're going to do here is we're just going to come back here. We have the same structure, but some things are going to be different here. So, oh gosh. So this is going to change. Okay, that's going to change. Oh no, that was a lie. Okay, that's going to be the same. This is going to change. This is going to change, and this is going to change. All right. So let's see what happens. So this time, instead of ending up with a speed of 2.5 meters per second, it ends up with a speed of 4 meters per second. So the initial situation is the same, but we have a new speed of 4 here. So what's interesting about this is it hits, and now when I subtract, I have -5. So this is actually -1 meters per second, which means that it would hit and actually move back in the opposite direction because the velocity is negative now. So that's important. But the initial side still stays the same. Let's look at the final side over here. So 1/2 m. What's the v of this one? It's 1. Now, I know it's -1, but we're going to square it. And this one is 4. Okay. So when I go to plug that in the calculator, okay, 4 squared is 16. 16 times 10 is 160, and half of that is 80. And over here, I have 1/2 of 5 is 2.5. So I end up with 82.5 is the new total energy. And what I'm noticing here is I started with 42.5, I end up with 82.5. So I'm somehow gaining 40 joules of energy. And somehow we'd have to add something to it. So someone pushed it, there was a little explosion when it happened. So there's some energy in a gravitational or magnetic field. So if you notice here that you gain a bunch of energy, you gain 40 joules worth. All right, 57. 57 says, in figure, a ball of mass m, 60 grams, is shot with a speed of 22 meters per second into the barrel of a spring gun of mass 240 grams. All right, I'm going to write these down because I don't want to forget. So the ball, m ball is equal to, what's it say, 60 grams. So again, got to work in kilograms. And the gun is 0.240. Now, sometimes, if you use grams the whole time, maybe it doesn't matter if you have grams on both sides and then cancel, but it's always nice to just work in kilograms. That way it's not a problem. The ball sticks in the barrel at the point of maximum compression of the spring. Assume that the increase in thermal energy is negligible. What is the speed of the spring gun after the ball stops in the barrel? So it's coming in and it's going to hit and stop. So we're going to use a conservation momentum situation. So PI is equal to PF. So I have mass of the ball times velocity of the ball is equal to the mass of the ball plus the mass of the gun times their combined velocity. So it says that the speed is 22 meters per second. That's fine, except for, let's put the mass in, so it's 0.06. The velocity is -22. So don't forget that momentum is a vector here. Let's calculate this. So the velocity of the ball and gun after is going to be equal to, so it's moving at 4.4 to the left. What is it? Oh, got the speed. What fraction of the initial kinetic energy of the ball is stored in the spring? So I like this question a lot, actually, because if you look at the energy situation, it says that the thermal energy is negligible, so we can actually calculate the total energy. So if we say the energy initial is just going to be the kinetic energy of the ball. So let's calculate that. So I got 14.52 joules. So what about the energy final? Well, what's the final energy situation? We have the kinetic energy of the ball gun plus the elastic energy stored in the spring. That's actually what we end up looking for here. So let's find this energy here. Ooh. So that's just 2.9. So the energy final is equal to 2.9 plus the elastic. And the thing is that if there's no thermal energy, the initial equals the final. So if I subtract, I end up with 11.62 is equal to the spring energy. So it says what fraction, what's it saying? What fraction of the initial kinetic energy of the ball? So the initial kinetic energy of the ball was, so if I do US divided by K ball, this is equal to 0.8, which is 4/5. And that's it for Chapter 9 Problem Set 3.